Hey there, welcome for those who just joined, and welcome back to Programmers Week for those of you who attended our Tech Talks and keynotes this week. Today we have the last day, and our main stage is machine learning in data stage. My name is Alin. I'm the community manager for mobile and AI communities, and I'll be your host today for the AI talks that our AI and other communities will present today. So let's start today with the first talk. We have here our talk about detecting asteroids by Raul. Raul is one of our Java developers in our, let's say, development community, but also he has a very strong passion about AI. And he wants to share his knowledge about a project codenamed CERES. So without further ado, I'll let him introduce the topic, and let's hope we have a very interesting day today. So let's kick it off with Raul.
Hello, everyone, and thank you so much, Alin, for the introduction. Thank you for joining us for Programmers Week. For those of you who may not know me, my name is Raul Urechiatu, and today I'm really excited to talk about the CERES project. I personally find it strange to have a slide about myself, so I left it out of this presentation. Instead, I'm going to talk a bit freely about why this subject suits me so well. From a young age, I found myself interested in everything related to astronomy, and as time passed by, it stuck with me. And I can say that I'm still quite passionate about it. That's why my favorite subject during previous years of study were the ones involving image processing techniques, as I thought of many appliances in satellite images. If we discuss about studies and you want to know more about me, I finalized my master's degree in artificial intelligence and distributed computing, and I'm currently studying for my PhD in artificial intelligence. Being so passionate about the astronomy subject, I applied for a project related to that, and that ended up being CERES. I think this is enough about myself, and from here on, I'll discuss some aspects of the project itself. Here we can see how the structure of the presentation is going to be. First, we will have a short introduction about us and the setup. After, we will discuss how things are currently done. Hopefully, this will help us transition to the next part, about the motivation of the project. We will define the problem here and some technical aspects related to it. Afterwards, we will present our proposed solution and what techniques we use to obtain the current results. In the last part of the presentation, we will talk about the results obtained. We will show some examples of asteroids from our data set, and lastly, we will present our conclusions. The total time of the presentation will be around 30 minutes, give or take, and as you may be used, we will have the QA at the end. Hopefully, this session will end with a fruitful discussion about this topic. Without further ado, let's get to it. CERES is a machine learning approach to near-Earth asteroid detection, as you may have known about. The project is done in collaboration with the University of Craiova and University of Cluj. While our work here at University of Timișoara was to develop the neural network, our colleagues in Cluj helped us get the best data we could out of nearby platform. Some information on the nearby platform will be presented soon. The last part of the project, which is the testing part, will be done by our colleagues. Sorry for this. Will be done by our colleagues from University of Craiova. We are using images gathered by La Palma telescope. I don't know if many of you heard about this, but you will see in the next slide. These images are formatted using the FITS standard, mainly used in astronomy. The FITS format takes in consideration the light intensity values, a property that we will understand better in a later slide. Here we have some beautiful photos of the La Palma telescope. Here is the place where several of our colleagues from University of Craiova live right now. They do so in order to have an easier access to the telescope and all the experiments it provides. I won't get into technical details of this observatory, as I'm sure they will be boring. But you know what isn't boring? The Canary Islands, where the telescope is located. And I assume that I'm not wrong when I say everyone would love a visit at the observatory here. So let's get to the current approach. So it is to use an asteroid detection algorithm which identifies objects in the image. Maybe you are wondering, but why do we need CERES then? So this approach is a more shallow one than what we propose, as it doesn't involve machine learning techniques. Also, it outputs too many invalid objects, and therefore users need to validate that manually. As you may think, it is really hard and sometimes even boring for them because the task becomes so repetitive. To answer the question how they are manually labeled, each asteroid we have the following approach. They use the nearby platform, as we can see in the following image. The nearby platform is the one that we talked in a previous slide. Here we can see three types of objects. The ones with the green background, which means they were validated by the users. The ones with the red background, which means they were invalidated. And the ones with the gray background, which are not validated yet and awaits user input on those. In this view, we can observe there are many information useful to validating asteroids. We plan on making this task so much easier by integrating our network in the decision making, thus having a pre-made prediction of whether the object is indeed an asteroid or not. In this image, we can observe many information that is used to validate the asteroids. A really interesting metric is the FWHM, which stands for full width at half maximum, and it represents the number of pixels found on the center, at the center of the image. You can see it right here. This center is represented in the slide as the crosshair from the asteroid picture, so this red cross here. The values this full width at half maximum should have are similar as in the example presented. So we see here that all of the information is around 1.4 or so. So we do not include such data in the prediction right now, but we plan on introducing certain values in the following versions. The automation process we propose is supposed to help the actual users to be a lot faster in reporting the actual asteroids. So in this section, we will discuss about the definition of the problem. To answer the question, why we need CERES project, we first need to understand how the current system works. After one night of observations by the telescope, there are thousands of images to be analyzed by the users. As we've seen on the nearby platform example, a user has to go to each object and label it accordingly. Having so many images to analyze can also lead to, you may have intuited it, lead to human error and affect the quality of validations. Now it takes around 24 hours for asteroid validation and reporting. This time means that other observatories can report an object that our team spotted first. You can imagine how much time that is when considering how many such teams of astronomers are working on the same task. So to be able to compete against the best from the world, we plan on automating this process as much as possible and reduce the time by at least 0.5%. I say 0.5%, but we plan on getting at most 2 to 4 hours for reporting. So I think it's even more than that. Also, the automation's goal is not solely related to time aspect, as it tackles the efficiency as well. For this, we want to compare how much easier it is for the user to have a detection already made for them. This comes in aid of reducing the number of human errors that exist on the detections right now. Sadly, we do not have a metric in that regard, but we know for sure from discussing with the colleagues that there are a few cases where human error really comes in play. What is the problem definition and with what are we actually working? We are currently using images that are cropped to a size of 200 by 200 pixels. For those of you who already have some experience with neural networks, especially the ones involving convolutions, this size brings some issues. But we'll discuss about how we tackle the problem at a later time and maybe even have some information related to why it is such a big problem. The images will always have the asteroid centered if they contain one. An image can also contain only noise, stars, or artifacts, and have no asteroid in them. This can happen because the telescope sometimes shifts a little bit while doing the four images, or have some issues with the lenses, maybe some spots around the lenses, so there can be multiple causes to this. There are usually 4 images per one object. I'm saying usually because some examples have only 3, but they are mostly invalid. We can see in the following examples how 4 images are resulting in a GIF in which we can clearly see the asteroid in the middle. We also have the star, which is stationary, but because of the technique of centering the asteroid that the telescope is using, we get the feeling that it is moving. This was created mainly to help the user visualize better the actual moving effect of the asteroid. The effect makes the detection much more easier and accurate compared to having only 4 separate images. Maybe you can tell us if it would have been easier for you without this GIF in the Q&A section. So right now, we will talk about the solution we came up with and how we plan on tackling the previous discussed problem. What we did is to build a dataset from the existing images and label them accordingly. This data came directly from the nearby platform and these databases. So we worked in the exact environment in which our tool will be integrated. After we gathered as much data as we could, then we started the work on training a machine learning model. Its job is to detect if an image contains an asteroid and integrate this model into the nearby platform. Its purpose is to work together with the user, making its life easier rather than fully automating his work. This is made on purpose, as we can see there are some special cases where a user is the best to decide the final answer. For the technical solution, we propose an ensemble model. Our ensemble model is created out of state-of-the-art models, and for its creation, we used the stacking ensemble technique, which is used to obtain reduced overfits. In the next slide, we will detail more on what an ensemble model is and about the ensemble techniques. Again, for those of you who worked with machine learning, this may be familiar, but for others, let's get into some details. An ensemble model is usually comprised of multiple models that work on the same job or on different jobs. We can think of this like, for example, we have a team of 3 members, and there comes a task that all 3 members need to work on. Well, the ensemble model has 3 approaches, but we will focus and discuss only about our current one, the stacking method. In this process, all 3 members work on the same task. And in the end, you compose a best solution out of all their work. So translating this to machine learning, we train 3 different models on the same problem. And in the end, we combine them into our final ensemble model, which is used for predictions. This helped us in reducing the overfits and gaining better results overall. So what we did, we took the same data set and we trained 3 different models with different architecture on the same data set. And afterwards, we combine the results. We plan on integrating a different approach where we have several data sets differentiated by filters, but on this approach, we will discuss on the future work section. We want to show you also what models we used for the previously discussed stacking technique. They are ResNet 50, Inception ResNet version 2 actually, and the exception model. Maybe you are wondering why we chose them, so let me tell you a few things about each. The first one is the winner of one of the biggest classification competitions from 2015. And you will find it everywhere while searching for the best classification models, especially for multi-class classification. The second one is the runner-up of the same competition, and it was also developed by Google. So I kind of put my trust on that one. I don't know if I should. But the last one is also the successor of the Inception model. So basically, it's what Google developed after that Inception first try. Even though they are kind of familiar and related, they are also kind of different in architecture. So each 3 of them have some differences in the architecture and provided more advantages to use them together rather than only one of them. We also tried an approach where we only used each of them individually, but the results were much more better when we actually approached an ensemble model as we proposed. Okay, so from here on, things will get a little more interesting. We will discuss about some pre-processing techniques. These were taken as steps before training our model in order to make the images more suitable for training. The first technique we used is the image stacking one. As we can see in the example, we take all our 4 images and stack them together to obtain a single image. Maybe you remember the GIF we had, where our asteroid was moving. Well, we try to replicate the effect as closely as possible, but on a single image instead of a GIF. This helps our network to have more precise information and make it more easier for the human eye as well to detect whether there is an actual asteroid or not. I think I'm safe to assume that this is much more easier for everyone to observe that there is an asteroid actually and not just noise or a star, as everything in the background seems to be moving. Again, because of centering the asteroid technique of the telescope. The second technique we used is the cropping one. This will answer to the concerns we had, if there were any, about the large size of our images. Do you remember that 200 by 200 images where we said there may be some problems? We decided this was necessary after feeding the full 200 by 200 images, resulted in high overfit and really poor training results. Image with lesser pixels obtain much better results, so we tried multiple sizes. In the end, we decided to stick with the 75 by 75 one. This pair was used because of a restriction of the inception model as well, but this was not affecting the performance, so we stick with it. So we basically needed to have the 75 by 75 if we wanted to include the inception model as well. But we deem that it's not necessary to reduce it even further, because that means that we will lose more information from the picture. This approach of cropping increased the recall from 60–70% to around 80%. So in the following images, we can see how different cropping sizes affects the outcome of our training. The orange line is the recall, and the brown line is the validation recall of the networks. So we really want to focus on those. It's mainly the 2 bars at the top of each graphic. What the orange line actually means to us is how our network performed in the training process. So not before finalizing the training and what we actually get. While the brown bar is exactly that. It is related to how well it did after the training was finished. So how it performed on actual results. From here on, we will introduce a new idea of the overfit. To summarize it, your intuition may have already told you that it is generated when training results have significant different values than the validation results. We can clearly see how spiky the brown bar is. That means that we have a high overfit in our results. In this first image, we can see the orange bar and brown bar are not at all linked. So that means a high overfit. It actually means that training was kind of useless or did not present good results for us. Yeah, so this tells us that our results are unpredictable and the training did not have a good outcome, even if the values are high on the orange line. Again, orange line representing the training period. From here on, our goal is to make them as smooth and as high as possible. In the last image, we clearly see that cropping had a huge impact in this issue, especially by the end of the training. So we can see here the lines are kind of higher, over 8%, 80%, and actually they are smooth. So the training had a really good effect on the data. Here we added a comparison between the initial image of 200 by 200 pixels and the currently cropped image of 75 by 75 pixels. There is some information in the background that is lost during this process, as we can clearly see in this example. But what our previous slide with statistics tells us is that that information was useless for our network and made it even more difficult to properly train. So this is a question for you to think about. Does more information always mean more power? For us, it certainly didn't. The next technique used is the augmentation. This was used to obtain more training data for our network. Currently, we work with around 40,000 images, which after the stacking process resulted in about 12,000. So there are many augmentation techniques. Most of them are pretty simple. Rotate the image, flip it, add some simple filters, and stuff like that. We used one of the simple ones for our problem, the rotation, by rotating the image by 90 degrees for 3 times. This resulted in around 45,000 images. There are more advantages to, there are more advanced augmentation techniques also, like adding filters on images or changing the pixel values, but those can also have unexpected effects. So we stick to the simpler ones. Also, we currently work with some filters that are not going to be included in the presentation because they are work in progress, but also they can be used as augmentation techniques, but we want to take another step on that matter. In the following example, we can see how an augmented image looks like with all its rotations. So we can observe that the information from the image was preserved mostly. It just helped us generate more data. And you can think of these like actual images because it could happen to have asteroids in this regard. Also, this kind of includes another problem into the topic. If we have some wrong information in the data set or wrong data, this also means that we have a dirty data set. And we actually do have some wrong information there. And by multiplying each image by 4 times, we actually multiply the wrong data we have by 4 times as well. So this is kind of a problem that we need to tackle, but right now we are working through it. So the last processing technique we used is the normalization one. This is used to obtain pixel values between 0 and 1. We need this because of the fits format that we discussed about in the beginning, if you remember. This format uses pixel values correlated to light intensity, so the values go as high as several thousand. Values like this make it really hard for our network to find similarities and train properly. So we looked for a way to make them more smaller values, ideally from 0 to 1, and actually preserve all the information in the image. So the normalization, we found did exactly that, and it works perfectly for us. Our goal for normalization was indeed to change the pixel values to an interval of 0 and 1 without actually changing the image itself. In the following examples, we can see how normalization process we used did exactly that. We now will have to work with lower values in the images without affecting the actual pixel range. So here in the example, we can see that, and indeed that's what's needed to happen. We have 2 images that looks exactly alike. So our normalization process did not actually affect it. I feel it is enough on how we did it. Maybe this is a time to ask yourself if you would have done it differently. If you do so, please let me know in the Q&A section at the end, because we also need to improve the application further. So all the suggestions you have, it may be really useful for our development. Without further ado, let's get to the results and analyze what we actually achieved. The metrics we used to understand our results are some classical ones for binary classification problems. Some of you may already have worked with, they are not solely used in artificial intelligence or neural networks. They are used everywhere where we have classification problems. Maybe you even heard of most of them. They are the true positives. That means our actual asteroids predicted correctly. True negatives related to invalid asteroids predicted correctly. False positives representing invalid asteroids predicted incorrectly. And last but clearly the most important for us is the false negatives. They are related to valid asteroids predicted incorrectly. So you can easier is to think of the false ones like what we did wrong and what we didn't predict, and the true ones on what we did good and what we predicted correctly. We want to focus a lot on the last one, as it is the most important for our problem. So I'm talking here about the false negatives. It is of such importance because let's think about it for a second. If you were an astrophysicist and your goal was to discover asteroids, I'm sure you would prefer our tool to not miss actual valid ones because your job is to find new asteroids, not to actually just label them correctly, the ones that are not actual asteroids. So yeah, of course, we want to focus on reducing the number of false negatives as much as possible. So we discussed about the, let's say, raw metrics. Let's talk about how can we use them to get the best understanding of our problem and the actual results we got. For this, we calculate a really important metric for us, the recall value. This is mainly used, as discussed previously, because it takes in consideration the false negatives. There is another formula that takes recall into account, that its name is F1, but also it is greatly impacted by the precision. So we ended up by choosing a simpler one. Yeah, this may be some simple information for those of you who work with neural networks, but it's not so pretty straightforward if you are not used to statistics and everything related to neural networks. So again, F1 is a more complex formula, and it kind of gives you more insight in different data and different metrics. So that's why we stick with the recall one. Okay, so maybe you ask yourself, what are the values of these metrics in our project, CERES? So let's see what we achieved with our current network. The results are recall values of between 85 and 91%. We don't have only one threshold for this because of the many variables that are involved in the training process. Also, we tested it on two different datasets. On these two datasets, we'll have a lot more information in the next slide, and you'll see exactly how each of them perform. False negatives, values of under 10%. This is exactly what we discussed as the most important metric for us, the false negatives. But 10%, these are really good values, but for now, we want to take them even further and achieve false negative rates of at least under 5%. Because let's think about it, 10% means that if we have 100 asteroids and valid asteroids, our tool would miss around 10 of them right now, which is kind of high for what we try to achieve. So we discussed about the two data sets in the previous slide. Let's see how each of them perform. In this image, the confusion matrices helps us do exactly that. We can analyze the results we obtained for those two data sets. The data set on the left has around 80,000 stacked images. So let's keep in mind that these are stacked images and not for images that are individual. While the one on the right has around 2,500 pictures. We can see on the bottom side of both how many good predictions our network had, and in the top left how many false negatives there are. These values can be found in parentheses, while outside of them we see a value from 0 to 1, representing actually the percent of each class. So for the false negatives, we have 5%. Or in the image with around 8,000 images. And true positives, around 22%, and so on. So if we remember about the metric that is really important to minimize, which I hope you guys know by now, the false negatives, we can see in the left dataset how good our network performed, as the values reach only 5% of the total dataset. This is exactly what we look for, but unfortunately, the second dataset proved us that our problem is not so accurate as expected because it reached almost 10% of false negatives. So that's why we want to further our understanding in the problem and develop it even further so we can reach really, really small false negatives now. Because maybe you ask yourself why the false positives aren't so important. Because let's say that we have 100 images again of asteroids, and we have, let's say, 10% again of false positives. That means that our network labeled them as being asteroids, but actually there were no asteroids in the image. And for a user to, and yeah, keep in mind that we have also the manually validation part of the users, in which they need to come in and actually validate these images. So that step kind of invalidates the idea of needing false positives numbers so reduced, because they can input their opinion on whether that it's actually an asteroid or not. So false positives are not such an issue. But false negatives, it's already missed data. So yeah, we want to minimize as much. Maybe you were wondering how our images actually look like. So we can observe in the following slides some outstanding examples from our dataset. I'm saying some outstanding because I try to find exactly I'd say the most difficult, but having thousands of images to go through, I'm sure we can find more difficult images to analyze. But here are some of the outstanding ones I found. Here we have some true positives. which, if you remember, were related to actual asteroids predicted correctly. In these images, we can see how difficult it may be even for the human eye to spot some of these. But more importantly, we want to point out how different the noise and the background of the image can be, because having such different tones for backgrounds may result in strange training of the data. But it was not the case, as we had good results on our outcomes. This can make it hard for a network to have the best training and prediction results. But yeah, it managed to actually perform really well, even with kind of hard background for a problem and a neural network training environment. Next, we will look at some outstanding true negative examples. These were the invalid asteroids predicted correctly. In some of them, we can see an object that somehow can trick the network in predicting it as an asteroid. To be honest, the top right one, exactly here, actually fooled me too when I looked at it. So it would not be so strange if the network got fooled as well. But it did not. And this was predicted correctly, and I'm quite proud of, of that. Another question arises if we think about the data set. Is it accurate? Can it be used as an absolute source of truth? So yeah, exactly the problem I discussed with you a few slides ago. To answer this question, we have the following two slides. And my input on this is that no. Even though in most of the cases the images are accurate, we have displayed certain examples when they are not. So most of the data here, I would say it's at least up to debate. So if you have any ideas related to these examples, please go ahead and let me know in the Q&A section. So I'm showing you exactly how it was actually labeled by the nearby databases and what our network predicted here. So yeah, I don't know, but for me, looking at the problem directly from here, it seems that these are at least worth a look look to them, if not predicted correctly as we did. So this means that we have a dirty data set, exactly as we discussed on the augmentation process. So another question, what's going to happen if we augment these examples as well? So maybe our results are not as bad as, or even our results are better than what we present, because if we augmented these wrong images, then we also augmented our results. So here we have some more examples on the problem that we previously discussed. Maybe these are even more concluded on the idea. For example, in most of these images, we can clearly see that there is an object in the middle, but they were still labeled as false. Maybe you are asking, why is that so? So this can be because a user may have labeled it as a star from experience or contextual. Remember that we cropped our images, so maybe here on the background there was some more information that human eye can spot easily. The question here is, would you want a more precise network reaching at higher accuracy rates at the cost of more false negatives? My answer to this is that I prefer the network to show these as valid ones and then to be invalidated by me manually rather than losing more actual asteroids. Exactly the problem we discussed when we talked about false negatives and versus false positives. So we are currently reaching the end of the presentation, and I think now is the time to have some conclusions. For this part, we want to emphasize on having recall rates of at least 80%, which is good, but also needs improvement. And also the ensemble model was really important in reducing the overfit of our network, and also a really interesting approach to neural networks. So yeah, of course, this was really cool. It provided a much needed experience for us. And also it's good to have solutions at hand. So ensemble model is a really complex one in which you include multiple models. So basically you have to work on different models at the same time and then combine them together. So this is a much complex, I'd say, not just solution, but also an architecture. I tried to actually include my ensemble model architecture diagram in one of the papers. but I think I needed around 4 or 5 pages of A4 to be able to include everything there. So sorry, I just need to take a sip of water. So you can think how big this ensemble model got by the end of our development. So yeah, it's a really complex problem, and it's really hard to understand exactly what's happening there. For the problems and future work, we want to reduce the overfit and increase the recall values even further. We want to gather more training images from the nearby platform. I think there are some experiments that were done in the previous months that we want to use as well in our training. And also decrease the number of false negatives to under 5%. We're working right now on different filters for the images, exactly as I told you in the previous slides, and we want to feed them to diverse models and assemble them in a final one. So we basically want to have 5 models in which we feed different filtered images. So we take one example, just take one example in mind with an asteroid. We want to apply certain filters on each of them. And from those filters, we want to be fed into 5 different networks. And we will use the ensemble techniques in creating a final architecture with those 5 models. But this is still work in progress. I don't want to get further into the details on what filters we are using on that, but we can discuss them on the Q&A section. If you have the time, it will be so important for me to actually leave a feedback related to this presentation and let me know how you felt. Let me know what I need to be improving, because of course there needs to be more improvements for the future presentation. And we want to facilitate this as much as possible. And I provided a QR code. This will link you to the form of feedback. Or you can use the link that is going to be sent on the chat by my colleagues. Thank you so much for that as well. This was all for me. And if you have any questions, now is the time. Thank you so much for your time. And I hope this went well.
Thank you, Raul. And yeah, good luck with your research further. We have a question. How do you cancel out the noise from the image, like some spots on the telescope? Even after augmentation process, they will still exist and hamper the data.
Yeah, this is actually a great topic of discussions. So if you remember, let me get to that slide again a bit.
Yep, sure.
So if you remember about the stacking technique that we used. So this stacking technique has multiple approaches to it. So we can stack the images by addition. So it means that we just take you remember the fits format we talked about, the light intensity one. So we have several thousand. So for fits format and light intensity, you can see here that these are some spots of lightning. That means that this is an object, an asteroid, a star, and stuff like that. So these values are several thousand of each. A star will have much more value. So addition on the stacking technique actually means that we add everything up and we get a final image. So right now we are not using the addition one, but the median one, which in literature, it's said to be the best approach for stacking technique in astronomy. So median one means that we kind of summarize all the pixel values and obtain the median value of all of them. And thus we obtain the stacked image. But that helped us remove certain parts of the noise. Sadly, we didn't manage to remove all the noise from our image, as you can see here. But right now with our filters, we are working on exactly that. So our filters uses some special techniques that are currently gathered by my colleague, which is working on developing that filters, on which we removed the noise completely. But that may provide some errors as well, because removing the noise, you can see here that the noise is formed out of white and blue and dark dots and black dots. So in some cases, that noise is really hard to be removed because it may provide fake images or fake information in the background. As you may find, if an image has a specific type of noise, that image can provide certain objects that are not really there. So yeah, this noise-related question is a really good one, as it is an ongoing problem that we try to solve. I hope this kind of answers the question, at least.
Yeah, and we have another question. And how can we calculate the parameters of the asteroids?
The parameters, yeah, that's a great question. So again, this is more done here on the nearby platform, and we don't tackle that much this information. So I'm guessing you talk about the full width at half maximum, which is seen here. So usually we take a threshold. So let's say we have a centered pixel. In our case of 200 by 200, it should be the pixel at value, I don't know, I think 50 by 50 or stuff like, or something like that. And we take a threshold. Let's say with a threshold, which means actually a number. So let's say we take 3, for example. If we take a threshold of a value 3, then we will need to provide and generate a kernel. A kernel is actually a matrix, and actually a matrix that's applied on top of our image. So if we have a kernel of 3 by 3, then it means that we have a matrix here on the middle. So we check in that current matrix if we found any light intensity values, let's say higher than another threshold 1000. So if we have light intensity in any of that matrix, then we calculate our full width at half maximum. If at the edges of the matrix, so the numbers at the edge, then if the numbers are getting smaller there, it means that we reach our end of our threshold. So we basically start to get a smaller number. So let's say if we have a threshold of 3 by 3, a kernel of 3 by 3, and all the light inside of it is present, we will have a number close to 1, because we will divide everything by the number of computations, not computation, but the size of the matrix actually, but so 3 by 3. And if all the information in the kernel contains light intensity that's above the threshold, we will consider it that it is a present an object in that part. So you can see here that exactly that it's happening, and there are actually different techniques. Another technique which uses a variable matrix. So the matrix just volumes up and gets bigger and bigger until there is no object. And it's actually a way to measure objects as well, that's increasing matrix. I don't know exactly about other metrics calculated here. I don't know exactly what E it's supposed to be, because this is not provided by us. So this is another project that's going nearby, and we are just working together to implement this validation process. So this is just additional information that we know about.
Okay. And how do you know how many images you need to stack to get the optimal image? Do you have a formula, or you just approximate?
Yeah, great question. The thing about as we discussed previously, we only have a set. I don't know exactly where the slide is, but let's get here.
Yeah.
For each object, the telescope. So maybe let's get into how the telescope actually gets this information. So its setup is to take 4 images of each object. So that's how the telescope actually gathers images. So it focuses one object that's supposed to be an asteroid or something that's moving. It gets one picture. Then it waits for 5 minutes. Afterwards, it takes another picture. It waits again for 5 minutes. It gets another picture. And it does so for 4 times, because there were tries and actually currently there is another technique that's being implemented for capturing asteroids, which exactly that's what another project is supposed to start about. So there are 30 images took at an interval of 30 seconds instead of 5 minutes. So we have 30 images at an interval of 5 seconds and of 30 seconds, and that means a much cleaner and smoother line in the background for let's say for the stars. But right now we only have 4 images. That's not a formula. We only check exactly because we know the name of each object. So we check for its name and see exactly how many objects there are in the data set for that object. And we always have 4 or 3 images, but not a much more different value than 4 or 3. So basically, we just check for how many images we have in our data sets or in our data store, and we compose those images, 4 or 3 or whatever. We don't have a formula for knowing, and we don't actually have more images on one object, only these 4 maximum.
Cool. Yeah, thanks for your answers. This is it for now. And yeah, great presentation, great project. Like it.
Thank you so
I
much,
think this
guys.
approach,
And
yeah, I think this approach can be used also in other detection of, let's say, celestial things.
yeah, I hope, guys, if you have any questions, please let me know. Maybe you can even mail me or send me a message. Please feel free to ask. And if you have suggestions, again,
Yeah,
please do so. It's really important for me to have as much feedback as possible in order to improve both the presentation and how I'm presenting stuff, and the project itself, because it certainly needs improvement. Nothing is perfect, and that's the only way we can improve, by receiving feedback from you.
true.
So thank you so much for your time and attention, and I hope that everything is good and you have a nice presentations ongoing as well, because today I hope it will be an interesting day for you guys.
For sure, data and AI is an interesting topic. So
Yeah.
yeah, I think you will join also the following text talks, right, Raul?
Yeah, I'll try as much as my schedule allows. I'll try to at least have them in the background. So yeah,
You
they
can
are
watch the
really interesting.
recordings also.
Oh, that's
Uh,
perfect. Yeah, yeah.
yeah. Thank you for your presentation. And guys and girls, see you in 15 minutes with the next one.
Thank you so much, guys.